For our next video, we're going to look into parent functions. So what is a parent function? A parent function is the simplest function of a family of functions. It's the most basic form of that type of equation. And then every other equation we see that's like that equation is just some transformation of it. Whether you move it, you reflect it, you make it wider, skinnier. It's just some transformation of that original parent function. The first one we're going to look at is linear. Okay, our linear parent function is y equals x. Right, now you should have seen linear in the past math classes, right? It's got that word line in it, right? And that's because our shape makes a line. Okay, so we're just going to make a table of values and plot our points for each of our parent functions that we look at. Okay, the table, I'm going to pretty much use the same 5 points, -2 to 2, just depending on what the equation is. All right, sometimes it's a little easier to skip ahead or to shift it to all positives, just depending on what we're looking at. All right, so if I plug in -2 for x, that will be y equals -2. If I plug in -1, it equals -1. Then we got 0, 1, and 2. All right, I'm going to plot these points really quickly. So we got -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. Okay, I have no restriction on my domain. I can plug in any x value and I'm going to get a y value. Right, so that's why my line goes in both directions. It's never going to stop. All right, the other graph is just for us to sketch another example or something else it could look like. So I'm going to make this one go downhill and have a negative slope. All right, and I moved it a little bit so it's not going through the origin, but that's just one of many, many, many options that we have for lines. Okay, a real life example we could have for linear, pretty much anything that talks about having a constant rate. All right, because this has a constant rate of change. That's our slope going up. It's the same rate that's going up. It's not going to change, or then it wouldn't be a line. All right, so for example, maybe if you make $2 selling each cookie, so $2 per cookie that you sell. All right, that would give you a linear graph. The next one is exponential. And this one's a little tougher, so I'm going to help us out with the table that we make. All right, we're just going to start with 0 and then go up to 4. Okay. Now our parent function is a little different. Now I've got 3 letters. Right? Normally we just have x and y, but now I've got this b thrown in. And that's because our parent function changes based on whatever that b is. That b is just our base. So you could have 5 to the x, you could have 1/2 to the x, 10 to the x, any number for b. Right? And whatever that b is, that b to the x becomes our parent function. Right? So the one that we're going to use to graph today is just 2 to the x. Right? And 2 to the x is very common, and it's a very basic one, so a lot of times people consider it a parent function or the parent function. Right? And this is the equation you use anytime you double something. All right? So I'm going to start with 4. All right? 2 to the 4th power, or maybe I'll start with 1. 2 to the 1st power is 2. Right? 2 to the 2nd power, 2 times 2 is 4. 2 to the 3rd power, 2 times 2 is 4, times 2 is 8. Right? And we got a pattern, we're just doubling. So we got 2, 4, 8, and the next one would be 16. Okay? 2 to the 0 power. Not sure if you remember this rule or not, but anything to the 0 power is 1. No matter what. 529 to the 0 power is 1. Right? So if I graph these, I got 0, 1, 1, 2, 2, 4. All right, and then I'm not going to plot the 4 and the 16, the 8 and the 16 just because they're going to get way up here where I've got my writing. Okay, but that just gets quickly super fast, right? So if I were to sketch this side, I know that it would kind of look like it's going straight up. All right, now on the left-hand side, okay, if it kept with this curve, you can see that it would kind of flatten out. All right, it's never going to cross that x-axis, excuse me. It's never going to cross the x-axis. Okay, at the x-axis is when y equals 0. Alright, there is nothing I can plug in to this x value that's going to make y equal 0. Alright, and there's some exponent rules that we're going to look at later down the road that help explain why. Alright, but all you need to know right now is that because I cannot plug anything in for x to get y equals 0, it's never going to cross. So if I put a little dotted line here, alright, that dotted line is called an asymptote. Okay, and the asymptote is a line that your graph approaches but never touches. Alright, and we draw it on all of our graphs whenever we're dealing with exponentials, but it's not really necessarily a part of the graph as far as drawing it. Alright, so it approaches but never touches. Every exponential graph has an asymptote. Right, and it's not always the y-axis, the x-axis. It just kind of depends on what your transformation is. It can move. Alright, so with that being said, over here, I'm going to make a new one. I'm going to put my asymptote way up here, because it can move. Alright, and your exponential can also be reflected. So I'm going to draw one that kind of comes up and looks something like that. But that's just one of many options as well. Right? A real-life example of exponential is bacteria. Bacteria, you might start with 1, and then it splits and becomes 2, and then they split and become 2, and so on. Alright, so if that were the case, that would also be something that's represented by this equation because it's doubling. But you also have accounts, your money, right? It's growing exponentially because you're collecting so much each year. You're collecting a percentage, and that overall amount keeps changing, so your percentage keeps changing. Our next one is quadratics. All right, a quadratic parent function is y equals x squared. You should have seen this one already. All right, so if I have my xy table, put those original 5 points in it. All right, negative 2 squared. Right, that's a negative 2 times a negative 2, so that's positive 4. A negative squared is always going to be positive. Negative 1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. Alright, so if I plot these, I got negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. Okay, if you remember, the quadratic makes this U-shape graph, and the U-shaped graph is called a parabola. Okay, very important that you know the correct terminology. Just like with the exponential graph, we can reflect this, and we can move it around away from the origin. So we could go anywhere like that, for example. Okay, a real-life example could be following the path of a ball that's thrown. Alright, if you think about it, it's not actually tracing the path, but if we have time going across the bottom and our height across the side, right, it might start at, 5 feet, if that's how tall you are when you throw it. Well, then as you throw it, it might get higher and higher and higher as time goes on, but then eventually it's going to come back and hit the ground. So it's sort of kind of following the path, the direct path, but not so much as like tracing it. Alright, so that's the path of a ball. Alright, we've also got the square root graph. Okay, square root is y equals the square root of x. Okay, this is the opposite of our quadratic where we had y equals x squared. Okay, because they're opposites, they're called inverses. Okay, this is the inverse of the quadratic. Alright, so I'm going to make my table. Alright, but I'm going to start with negative 1, okay, 0, 1. I'm going to skip to 4, then I'm going to go to 9. Alright, just to help us out a little bit and get some nicer numbers. Okay, so if I start with 0, the square root of 0 is just 0. Square root of 1 is 1. Square root of 4 is 2. And the square root of 9 is 3. Okay, now I skipped over the negative 1 because if I try to take the square root of negative 1, I can't. We can't take the square root of a negative. So remember, a negative square is a positive. So there's no way that I can end up with a negative. Alright, so that means that it's not possible. Okay, so I'm going to go graph this. I got 0, 0, 1, 1, 4, 2, and I'm going to stop there just so it fits better on my graph. Okay, so if I connect these, I kind of get this curve going up and flatten out a little bit. I can't draw anything over here on the left-hand side because I will never have a negative value. Alright, I cannot plug in a negative x. Okay, so it's not an asymptote or anything because I have this value at 0, 0. I just don't have a graph to the left. Alright, this shape we call it a swimmer's arm. Alright, that's how you can help memorize the square root. It's a swimmer's arm shape. Alright, it can look like anything. You can technically have, depending on your equation, have values over here to the left, especially if we were to reflect it that way. Alright, so real life examples for square roots. Okay, sometimes if you're dealing with speed, okay, we can't really have a negative speed, and the real big one is distance. Alright, we can't have a negative distance. Okay, so you might have just the square root of a number, but we would never have a negative that we plug in for that distance. Alright, and our last one is absolute value. Okay, absolute value is y equals the absolute value of x. That's what these bars mean. Right? Absolute value just means distance from 0. Okay, so the absolute value of something will always be positive. Alright, because I will never have a negative distance. Alright, so if we make our table, -2, -1, 0, 1, and 2. Okay, -2, if you imagine a number line, alright, here's 0, here's a -2. It is 2 units from 0. So that's how far the distance is from -2 to 0. Okay, -1 is just 1 unit. 0 is 0, so it's 0 units away. Then you got a +1 and a +2 that are just 1 and 2 units away. Alright, so if I graph this, we've got -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. You might remember absolute value makes a V shape, which you can remember by value. Okay, and another example, just like the quadratic, it can be reflected, it can be moved around, so you might have something that looks like that. Right, very similar to the square root. Okay, your speed will never be negative. Okay, so your absolute value, if you're talking about how far apart your speed is from somebody else, you'd use the absolute value, because even though you are technically 15 miles per hour slower, you would put a -15, you would just say 15. Alright, and then that comes in sometimes too with distance, and then with money. Alright, sometimes you're not necessarily looking at the deficit as much as you are just how far away you are from where you should be. Alright, so those are the 5 parent functions we're going to look at, and we will go more into transformations in our next class.